All right, so here we're going to talk about combinations where the order doesn't matter. And they have a pretty good example here. You get 5 cards out of a deck of 52 cards, and if this was a permutation, then the order would matter. So you can arrange these 5 cards in, well, as many ways. Well, that's actually 120, right? 5 factorial. However, it really doesn't matter what order you have. It's still the same hand of cards. And as it says, in most card games, that's the case. It says it right here, most card games down here. So if I calculate these here, I have 52 cards, and I'm going to take 5 out, and here we go. We get these 311 million permutations, but the combinations, because the order doesn't matter, is much, much smaller. And notice that these two formulas are really similar, except on the combinations we divide by 5 factorial, because the order again is not important. So we divide by that 100. Remember that 5 factorial was 100. You can check that any time. So again, the order doesn't matter. Of course, for the player, notice that the player actually did put them kind of in order. So here are the spades, and here are the hearts, and there are 7, 8, 9. So the player used one of the many permutations, I guess these 120 permutations, just to make it look better for them. All right, down here, what I did is, as they're asking questions, what's a permutation and what's a combination for these particular examples, I tried to underline them. So I underlined these here with green if it's a permutation where the order is important, and I lined it with this bluish color where the order is irrelevant. All right, so here we have a few examples. And sometimes it's not quite clear, so you have to look at it. So a social club selects 3 members to form a committee. Equal share of responsibility, that kind of gives it away. There isn't any order here. It's an equal share, so each one of the 3 has the same responsibility, so it doesn't matter who's who. So it's a combination, rather, a permutation, which means much, much smaller. For the password, well, the order, even though it doesn't say so, but the order definitely matters. Okay, so you take the same 10 letters for your password, and if you scramble them, well, it's a totally different password, and you scramble them again, totally different password, and you have all these permutations, so definitely that matters, and that would be a permutation. First, second, and third place finishers, that kind of gives it away. That's a permutation. Here you have to look at the entire sentence to figure out, oh, special of the day. It really doesn't matter how I arranged my 3 sides when they're presented. So it's a combination. Of course, maybe I'm particular, so I want to put these 3 sides in a certain order. Now I got a permutation. But usually when it's served, it's a combination. And then they have other examples here. So on Halloween, as the kids are coming, they each get 3 pieces of candy. It doesn't matter in which order you give these 3 pieces of candy to the kid. It's the same. Maybe they want to decide later they want to eat this particular one after another, but that's up to them. Here, your instructor chooses half the class to take the first vehicle, and seating them in there doesn't really matter in which order they are, so it's a combination, unless, of course, somebody decides, okay, this one person is going to get shotgun, and this person is going to sit on the right or left. Now it would matter. But the way this question or this statement looks like here, it really doesn't matter, the order. All right, I'm going to skip this one here, even though what they're trying to do is they arrange all these, 60 different permutations with these colors, and notice that the CED, DEC, EDC are all the same as far as the combination is concerned, because they're all the same letters. So they're getting here from, these are all the 60 permutations, but if you arrange them in these color groups here, then it really whittles itself down to just 6 different combinations. Or hold on, I think it's 10 different combinations. All right, I'm going to get to this formula here. Respectively, you have already seen it. All right, and a number of these questions, by the way, are actually just decide which ones if it's a permutation or combination. Others, in this case here, where you actually do the calculations. So notice here, 52 and 2, 21 and 6, 38 and 5. So Texas Hold'em, 2 cards out of 52, right? The Clue deck, which is a game, a board game, 21 cards, and you take out 6 cards, so the 21 and 6. And then the lottery, you take out 5 out of 38, and notice the results here. So I want to put this one over here, and I push this to the side so I can look myself at these here. So the first one was Texas Hold'em, 2 out of 52. There we go. That's if you check 1,326 was the answer there. And then this one here is the Clue game, the 54,000. You will see that in the book. And then the other one was the lottery, 5 out of 38. I was thinking if I could share some images here, but gosh, I didn't really find copyright free images, so I just left it out. And yeah, all these combinations here for the lottery, because it's 5 out of 38, 500,000 combinations in this particular lottery. And here, as the numbers are being picked out of 38, at the end for any kind of lottery, the order doesn't matter. And then they usually put them actually in ascending order, for example. All right, let's see. Again, you can look through these here and decide, oh, I already underlined it, that these apparently are combinations. And I boxed in some of these here, just some tidbits on the side. Let's see, this one here, I said something about a Rangers soccer team, so let me show you that. And I mean, what they do here is this committee with 8 people from this group, and then they choose 2 out of 10 seniors, they get 45 possibilities, 2 out of 8 juniors, they get 28 possibilities, and so on. And then what they do is they multiply these possible combinations here, and they get these 113,000 possible committees. So let me show you that with a soccer team, just because I want to. All right, so here's the soccer team that I want to use for that. And a soccer team usually consists, not usually, always consists of 11 players. This one here is the German squad for the European Championship in summer of 2024. And there's a total of 27 players that are nominated. And 4 of them are goalkeepers, GK. And then there are all these defenders here. I'll count them in a moment. And then there are these midfielders. And then there are these forwards. These are strikers. They're supposed to make the goals, actually. So for a soccer team, it's pick 1 out of 4 goalkeepers, 4 of the defenders, 3 of the midfielders, and 3 of the forwards. So I'm going to write that down. Let's see. There we go. All right, so on the German team, goalkeepers, there are actually 4 goalkeepers, and only 1 is chosen. And by the way, we know that pretty much. You can only have 4 different combinations, 1 out of those 4. And then there are defenders, defense, and I counted there's a total of 9 in there, and they take 4 out of them, and this would have to be calculated. I counted the number of midfielders, and there's 9 of them, and you usually take 3 onto the field. I hope I said that earlier. It depends on how you field your team. And then there are the forwards, and on the German team there are 5, and they also take 3. Okay, so these would have to be calculated, and this is the way to do it. I'm going to skip the goalkeepers because that's really easy. So I'm just going to do the, for example, the midfielders here. So for the midfielders, the combination is going to be take 3 out of 9. So you have 9 factorial. Then divide by, in parentheses, 9 minus 3 factorial. Now, if that was all, that would give us the permutation, and now it would mean that it matters in which way you put these three midfielders in midfield. But for just fielding them onto the field, it doesn't matter. The permutation doesn't matter. So you divide actually by the 3 factorial, which is 6, because you just want to figure out, well, how many different combinations can you put on the field? So that was now the combination, and again is the difference between combination and permutation. So now I'm going to compute these, and the 9 factorial, we had that at some point. That was a really big number in the hundreds of thousands. So I have to find the factorial sign here. There we go. So yeah, 362,000. And the 6 factorial, I kind of have that memorized. That's 720. There it is. That's the 9 minus 3 down here, factorial. And then the 3 factorial, well, that's one of the first numbers. We kind of know that is actually 6. 1 times 2 times 3, right? So basically, it's the 362,880. Let's see, I have one too many zeros, right? There we go. Divide by the 720, that would give us the permutations, but then divide also by 6 because the order doesn't matter. So here we go, 84 possibilities. And if we look at this one here for in this calculator, so this was 9 and 3. And there it is. The 84 combinations is what we need. In the meantime, I can also put then 4 out of 9. That's for the defenders. There it is, the 126. And then I can put that for the forwards. There was 3 out of 5. There we go, 10. And then I can put that for the goalies here. I already know the answer. 1 out of 4 is... Did I say 1 combination earlier? Hopefully I said 4, didn't I? Let's see. Oh, I grabbed the wrong one here. Yes, I did say 4 earlier. There it is. Okay, and then I can go in here and jot these numbers down. So 126 here, and then 84, and then 10. And then just like the example here for seniors, juniors, sophomores, and first years, how many combinations for this particular soccer team? Well, it's going to be 4. Oh, I forgot to write this one here down. 84. There we go. So it's going to be 4 times 126 times 84 times 10. By the way, this little dot here doesn't matter. That's just my hand touching the screen. There's another little dot up here. There we go. All right, so I'm going to get equals, and I'm going to pull out the calculator. So, in this way, you have also seen how to do combination on a piece of paper. But of course, I also showed you that there's plenty of online calculators that save you some work there. So enter here. So these are the number of combinations for the German soccer team. Now my calculator went away. I can't look at the result. There we go. At least I can look at it and copy it. I have a pretty big screen that allows me to do that, but I have to be able to look at it. There we go. So combinations for the German soccer team at the European Championships. Yep, combinations, permutations, they give you really large numbers. All right, let's look at the rest of this. Again, I have underlined what I think, I'm pretty sure what permutations are and what combinations are. So when your little brother is packing for a family vacation, only room for 3 toys. Well, it really doesn't matter how he arranges the 3 toys in the luggage. So the permutation doesn't matter, it's only a combination. Unless, of course, the little brother decides, well, these 2 toys I want to put in the luggage, and this one toy I want to take into the carry-on. Okay, now a permutation could matter, right? But other than that, whenever you're planning for a trip, it really doesn't matter in which permutation you have them, in which order you have them. Same, we had this one here with the friends earlier here. There's another packing for a vacation. And then here we're back to first turn, second and third turn, and so on. So that's a permutation. Top 3 for the finish, permutation. Working in groups with your classmates, groups of 4 with your classmates. How many possibilities? Well, it's a combination unless you have a certain seating order, but you probably don't when you work in groups. Or unless actually you assign certain tasks. Everyone has a different task. Now it again kind of matters. But the way it's worded here, it's a combination. So professor here choosing 3 students here. It doesn't matter in which order they go. They just present 3 different solutions. So it ought to be a combination unless everyone is getting assigned a certain homework problem or getting into a certain order, then it would be a permutation. I think this one here looks like a combination as well. The eliminated contestants, 10 of them are eliminated. How many of these combinations are possible? Well, it doesn't matter in which order they are eliminated, unless you want to keep track of it. But other than that, they're all just eliminated, so it doesn't matter. All right, and here I'm making an example. Instead of this card game Euclid that I don't know, I used the German Skat, which is the national game, and here it is. I found this applet not too long ago, and in this German, it says right here, Skat is the national card game of Germany. That's actually true. This is all in English, interestingly. And we have 32 cards in the game. There is, sure, whatever that means. I know what it means, but anyway, so we got 10 cards in this game. And I know now it's 12 because there's something on top of that. I have to focus something that I didn't want it to do. It's okay. So it takes 10 cards out of 32. If you look closely, what is missing is the 2, 3, 4, 5, and 6 from a typical card deck that is used in the US. So in Germany, it's only 32 cards, and we're taking 10. If you count these here for the opponents, they each have 10. And so it's 10 out of 32. The order doesn't matter. Of course, the player is still putting them in a certain order, just as one permutation there. But overall, it's a combination. It doesn't matter in which order these are dealt. It's still the same 10 cards. So basically, what we're getting is, for the first player, is 10 out of 32 are dealt. There we go. These, 64 million combinations. I'm typing that here onto the calculator on the side. And this is just the combinations, not even the permutations. And then for the second player, well, 10 of the cards are gone, so only 22 are remaining. 10 out of the 22. So for the second player, there is 646,646, interestingly, repeating there. And then for the third player, now only 12 cards are remaining, so there are only 66 possible combinations. These 66, you can come up in a different way, and that is saying, okay, for the 2 remaining cards, there's only 12 possibilities for the first one, and for the second one, there's only 11 possibilities. 12 times 11 is 132, but the order doesn't matter, so you divide by 2 factorial, which is 2, and that's how you get to 66. So the third hand is then 66, and again, 2 are remaining, and again, the order doesn't matter for them, and there's only 1 combination left for them. Here, I'll show you that. For the remaining 2 cards, it would be 2 out of 2. There we go. And there's that 1. There's only 1 possible combination. So here we go. I can just multiply that with the 1. I get this really huge number. So there's 2 times 10 to the 15. I believe that's in the quadrillion. 2 quadrillion possibilities for the game of Skat being played on a German Skat table. And it's just immense how many combinations, or combinations in this case, or permutations there are. All right, so I'm going to get this one over here. And yep, that was actually it, but I do have a couple more things. All right, so as I said, I'm going to take this a little bit further, and here's something. How many ways can the letters in Mississippi be arranged? And then this is from this particular website. By the way, if you want to look at the address, there it is. I think, how did I Google it? That's how I Googled it. Arrange letters, rearrange letters, and so on. Okay. And I also will have the word Antarctica there in a moment. And so this one here basically says, well, you arrange the letters, there's 11 of them, but a number of them are repeat letters, such as the I appears 4 times, and the S appears 4 times, and the P appears 2 times. So you have to divide them out, and then the M actually only appears once, and then the combinations are, or permutations in this case, permutations are 34,650. And then they put a little note here. Permutations and combinations is a very tricky chapter, and one needs a lot of practice for it. Maybe I should have started out with this one in my lecture here, but I think you noticed that. So anyway, so let me look at these here. I found this word here, since I already used it, the word copyright in here. And how many possible permutations could you have there? Notice there are 9 different ways of doing this. So the permutation is going to be, well, 9 out of 9, which is basically 9 factorial divided by 9 minus 9 factorial. Ooh, here's an interesting one. Look at this. Turns out this is actually 1 0 factorial. And there are reasons behind that. And I put that somewhere in the homework quizzes, and there are certain proofs for that as well. And so basically this one here comes out to 9 factorial, and we had that several times. I'm going to turn on the calculator again. And I used my own calculator earlier, but I think I kind of set, here's the Google calculator. All right. So here we go. So we have 9 factorial. There it is. 362,880. We did have that before. There we go. Possible combinations. We're going to look at the word pale. So that would be 4 out of 4. Basically, it's going to come out to 4 factorial. Oops. On. What I want to click on this one here. This is kind of smearing around. Let's see. Back here. So 9 factorial. No, 4 factorial is what I said. I just want to write it a little bit over here. We already know that 1 times 2 times 3 times 4, 24. Particular ones. Okay, so now this one here is new. So this one here we cannot use with the normal permutation or combination. So what we do is the number of ways this can be arranged is to take 4 different letters. So the 4 out of 4 permutations, which is 4 factorial. But then it turns out the P appears twice. So we have to divide by 2 factorial. And then the A also appears twice. So again, we have to divide by 2 factorial. So here we go. And then basically we're going to have 24 divided by 2 and divided by another 2. And of course, that's going to be 6 possibilities. Keep that in mind, because in a moment, in a minute or so, I will talk about some kind of swimming arrangement where the answer is actually 6 possibilities. All right, let's look at the word Antarctica. So the number here is that we have 3, 6, 10 letters. So it's 10 out of 10 for permutation. but then the letter A appears 3 times. So as I try to do the permutations, I have to divide by 3 factorial or 6 because the A's are identical. And let's see, do I have any others? There's an N, oh, the T, all right? So divide by, there are 2 T's here, so I have to divide by 2 factorial. And I think the others are unique, am I right? There's an N, there's an R, there's a C, there's an I, N, R, C, I. Oh, there are 2 C's. There we go. So another 2 factorial. So here I have 10 out of 10, which is basically just 10 factorial. And then I divide by 6, and then by 2, and by another 2. So here we go. So 10 factorial equals divided by 3 factorial, which is 6, divided by 2 factorial, which is 2, divided by 2 factorial, which is 2, enter, equals 151,200 combinations. And finally, the Mississippi. So the number here is, it has 4, 8, 11 letters, 11 permutations, and the S appears 4 times, so divide by 4 factorial. The I appears 4 times, the P appears 2 times, and there's only one M. So 11 factorial, divide by 24, divide by 24, divide by 2 equals, and again, my hand is kind of putting these little extra dots there. So when I do that, 11 factorial, pretty big number, right? Is that 39 million, I believe, divided by, let me check that, 24, 24, and 2. So divide by 24, divide by 24, divide by 2, there we go, 34,650. And when I check the website, if I'm finding it again, actually, then yeah, here it is, permutation, combinations, and so on. Oh, 34,650, there we go. All right, and then finally going back to this opening picture here with the swimming. So, and what I said here in this box here, watch the videos at the Tokyo Mixed Relay and the London Men's 100-meter final, and then the tryouts for the same Olympics, actually. And again, I'm not allowed to share any one of those videos because of copyright issues. So I'm just going to show you these tables here. So this is from the 2020 Summer Olympics in Tokyo, which was actually because of the pandemic held in 2021. And I really like this mixed 4 times 100-meter medley relay. And the medley means they're swimming the backstroke, the breaststroke, the butterfly, and the freestyle. And for each team, there are 2 women and 2 men. So it has to be exactly those. And you can put them in any kind of arrangement that you want. I'm going to go down to the final. There we go. And now I wouldn't know the Chinese names. So let's just look at the winners here, Great Britain. So notice that they have a woman, then a man, then a man, then a woman. All right. Now we look at Australia. They actually have the same thing. Woman, man, man, woman. Italy, I think we can look at that. Thomas, Nicolo, Elena, and Federica. That means 2 men first and then 2 women. The Americans, Ryan, Lydia, Tori, and Caleb. So they have a man, woman, woman, man. And I think we can also look at the Netherlands here. So Kira, Arno, Niels, Femke. So woman, man, man, woman. There we go. And so any kind of arrangement that they want, and they have to decide which one they do. And sometimes they might even have to leave out one of the best in the world because they need one from the other gender for this particular part of the relay. So how many possible ways are there to arrange 2 women and 2 Men, by the way, I already gave the answer away a few minutes ago with the example from Papa. Notice 2 P's, 2 A's, 2 M's, 2 F's, that kind of thing. All right, let's look at, I believe this one here is the Summer Olympics. By the way, Wikipedia images are copyright free once they're there, Creative Commons. So let's see, let's find the results. Maybe they're already here. Men's 100 meters. What happened to the results? I thought they were here. Oh, these are the heats. Okay, so I have to go all the way down to the final. There we go, semifinal, there we go. So here, of course, it matters who is coming in first, second, third, gold, silver, bronze. So you have to use a permutation on this one here. Before, Usain Bolt, Ewan Blake, and Justin Gatlin won the 3 medals, so you have to do a permutation, 3 out of 8. Notice that there were 8 starters on this one. And then finally, this one is the trials for the same Olympics, so the US trials. And you will see one name that was already there, Justin Gatlin, the American who placed for the bronze at the Olympics. I know they say gold, silver, bronze here, but in order to qualify for the Olympics, you really only have to be in the top 3. So for the trials, to get to the Olympics, it doesn't matter how you place in the top 3, it just matters that you place in the top 3. So a combination would be here, 3 out of 8 for the combination. So quite a bit fewer different ways on how to arrange them. By the way, in my opinion, the US trials are quite brutal, and I guess for a reason they are, because they have such great 100-meter runners that you could have the world record holder in 4th place in the US trials, and he's not going to make it because he didn't place in the first 3. It did happen to Carl Lewis 32 years ago, I think at the 1992 Olympics, where he only placed 6th. He was still part of the relay team, just not in the individual one. All right, I think that's finally it for this lecture.